Good day and welcome to the first part of our discussion on related rates. Now, related rates are one of two big types of word problems we will encounter throughout the semester. And in the past, students have always described related rates problems as being challenging. And what that indicates to me is that we really need to emphasize kind of the ideas kind of guiding us through how we approach these problems and really emphasizing kind of the thought process and the procedure we use to approach them. So the big idea behind related rates is we want to relate together two rates of change. That is, we will compute the rate of change of one quantity in terms of some other known rate of change. And what I'd like to do is start off with a motivating example that really makes this hopefully as clear and as easy as possible for us to see. So if we know x and y are differentiable functions of t, and they're related by some equation, what we would like to do is find the rate of change dy dt precisely when x is equal to 1, given that dx dt is equal to 2 when x is equal to 1. And we will have a very nice procedure that we can use or thought process to approach these problems. Whenever possible, draw a picture. Here there's no obvious picture that jumps out to us, but in every other related rates problem, there will be a picture that we draw. We write down the quantities that we know, and we write down the quantities that we hope to find. So in this case, we can say that what we know is that the rate of change dx dt when x is equal to 1 is equal to 2. And note the notation, dx dt vertical bar subscripted with x equals 1. That's telling us this rate of change when x is equal to 1 is equal to 2. So we want to use that good mathematical notation. And then we write down kind of precisely what it is we would like to find. What I want to find in this problem is what is dy dt when x is equal to 1. And our approach for doing so is to take the relationship between x and y, this equation y equals x squared plus 3, and somehow get derivatives to fall out of this, dy dt and dx dt. And the only way we can make that happen is if we differentiate both sides with respect to t. And note, when we differentiate y with respect to t, or we differentiate x with respect to t, that will be an implicit derivative, which was our previous topic of discussion. So what I'd like you all to do is to pause the video for a moment, differentiate both sides implicitly, and determine what is dy dt when x is equal to 1. And now that you've hopefully paused the video and finished up the problem, let's go through the details together. We differentiate both sides implicitly with respect to t. So that would simply be dy dt on the left. And on the right, working from left to right, we would differentiate x squared implicitly. So exactly as we would like. And because it's an implicit derivative, we need to multiply by dx dt. So kind of that rule of thumb for implicit differentiation. And the derivative of 3 with respect to t is 0. And now we are exactly where we want to be. We would like to know what is dy dt when x is equal to 1. So dy dt when x is equal to 1 is equal to 2 times 1. And we know that dx dt when x is equal to 1 is going to be equal to 2. And this is all equal to 4. And that is the desired rate of change that we are looking for. So note, overall, once you have this equation relating the two quantities, it comes down to differentiating implicitly, isolating for the rate of change you are interested in finding, and substituting in the specific value you want to know something about. Now, unfortunately, or maybe fortunately, because it'll be more interesting, We typically are not given this equation, but we are given enough information that describes some physical phenomena that we can draw a picture, introduce notation, and set up that equation that we're going to work with. So let's move on to what I would consider a very typical related rates problem. What we are told is a 10-foot ladder rests against a vertical wall. So as I claimed previously, I'm going to draw a picture, hopefully illustrating this scenario. So we have a wall and the ground, and we have a ladder which is 10 feet long, leaning against the wall. We are told the bottom of the ladder slides away from the wall at a rate of 1 feet per second. So I'm just going to go ahead and just note that the bottom of this ladder, so an arrow indicating away from the wall, and it moves away at a rate of 1 foot per second. And note, just for fun, when that bottom of the ladder is sliding away from the wall, there's no possible choice except for the fact that the top of the ladder would also be sliding, in this case, down the wall. And what we would like to determine is how fast does the ladder slide down the wall when the bottom is 6 feet from the wall. And the first thing we need to do after drawing this picture is introduce some variables. Whatever quantities are changing with respect to time, we should label with a letter or symbol. And in this case, I'm going to go ahead and I'm going to let x represent the distance that the bottom of the ladder is away from the wall, and then simultaneously we'll let y represent the distance which the top of the ladder is away from the ground. Now what we want to do is think about what do we know and what is it that we want to find. And as I mentioned previously, this is something that I need to see in each and every related rates problem. And the reason for this is, in order to solve this problem, we are going to need to know and be able to identify what information is given and what it is specifically that we want to find. And by forcing you to kind of write that down right at the beginning of the problem, I'm hoping it will help you to solve the problem a bit more efficiently. And also, it's a good opportunity to get some easy points right at the start of the problem. So think of it as a win-win. So let's think what we know in this problem. We are given the information that the ladder slides away from the wall at 1 feet per second. So pause the video and write down for me, what rate of change do we know something about? And hopefully you've written something down now. Note the information we are given. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. Well, x represents that distance the bottom of the ladder is away from the wall, so that is describing precisely the rate of change of x with respect to t, and we are given that it's always 1 foot per second. What we would like to find is how fast does the ladder slide down the wall when the bottom is 6 feet from the wall. So what we want to find is dy dt, and we want to know what is dy dt when the bottom of the ladder, so represented by x, is 6 feet from the wall. And a couple key things to point out. This information here, x equals 6, this is going to be the last thing that we use. We are going to use this at the last step. It will be tempting to try to substitute that in earlier, but fight that urge, and remember, substituting in x equals 6 should really be the last thing that you do in the problem. What we now need to do is get that equation relating x and y. Because we know dx dt, we want to find dy dt, We need some equation relating those two variables so that we can differentiate it implicitly. And when it comes to determining this equation, which is going to be a difficulty related to these problems, we can really use anything from our past experiences related to geometry, trigonometry, algebra in general. And in this case, hopefully what you're noting is that there is a right triangle hiding in our picture. And pause the video for me and write down what is the relationship relating x and y, the two legs of this right triangle, to the hypotenuse 10. And hopefully what you indicated is the Pythagorean theorem. X squared plus y squared is equal to 10 squared. Now that we have this equation relating the variables, we're good to go. We can differentiate this implicitly with respect to t. On the right-hand side, we get maybe the easy derivative. The derivative of a constant is always 0. But on the left-hand side, the derivatives are pretty quick and efficient as well. Each derivative that we see is going to be an implicit derivative because x is a different variable than t, y is a different variable than t. So if we differentiate x squared implicitly, we differentiate it exactly how we would like to, 2x, and then we multiply by dx dt. Similarly, to differentiate y squared, we differentiate it exactly how we would like to, 2y, and it's implicit, so we multiply by dy dt. Now that we've differentiated implicitly, we go back up to the beginning and we think, what rate of change do we want to find? And then we go ahead and we isolate that. So I'm going to try to leave the dy dt term by itself on the left. So we will subtract 2x dx dt from both sides. And note, the previous step we could have done so as well. We can divide everything by 2. And then we can isolate that dy dt by dividing by y. So minus x over y dx dt. And now we are at kind of the key part of the problem. What we want to determine is what is dy dt when x is equal to 6. And if we just look at our above equation, we can start substituting in values. X is 6, and we know from above dx dt is always going to be 1. So I can replace that with a 1. But that does leave kind of this blank that we need. What is y? And this is going to be a very common occurrence. We need to go back to our original equation and use the information x equals 6, in this case, to determine y. So this is just a little bit of work that we can do to the side. So note, our original relationship between those variables is x squared plus y squared is 100. So we think when x is 6, what does that force y to be equal to? So 36 plus y squared is 100. Y squared is 64. And typically what we would do is we'd say y is equal to plus or minus the square root of 64, which is 8. But remember, in our problem, y represents something that has physical significance. The variable y represents how far the top of the ladder is above the ground. So by definition, it has to be a positive quantity. So the y in this case is going to be 8. And what we are searching for is a rate of change of y, and y is a distance, so its units are going to be in terms of distance per time unit. Distance in this problem is measured in feet. Time units are measured in seconds. And we now have the desired rate of change. I do want to make a couple quick observations. The first of which is, as claimed earlier, this x equals 6, where we want it to know dy dt, that was used in the last or the final step. Secondly, I want to note that getting a negative here for the rate of change should make sense. Why does it make sense in this problem that the rate of change of y is negative? And the quick answer is, well, y represents a quantity which is shrinking or decreasing. So as the ladder slides down the wall, y is getting smaller. So the rate of change of a quantity which is decreasing should always be negative. That's a very important thing to keep in mind. Lastly, what I would like to observe is that there's kind of an overall procedure related to these problems. As we read through the problem, we draw a picture. Any quantity that changes with respect to time, we label with a variable, some type of letter or symbol. We write down the rates of change that we know and the rate of change that we want to find. Then we find some relationship or equation relating those variables. And once we have that relationship, we differentiate it implicitly, and we isolate for the rate of change that we are interested in. And the last and final step is to substitute in that specific value. But note, when you substitute in x equals 6, that may require you to go back to the original equation and solve for some other corresponding values. And we will continue on investigating examples in the next few videos, but as usual, this is a great opportunity to go through some of the suggested problems and practice on your own. Related rates problems in particular require a lot of practice. It is very difficult to watch or listen to someone else solve one of these problems and just immediately say, oh, I get it. You really need to spend that time on your own to truly understand and feel comfortable with these problems. So remember, when you have questions, reach out. Otherwise, stay tuned and take care.